if we recall, the last thing that we did on Wednesday was we started to talk about the three different types of electrolytes. Remember, electrolytes are substances that can conduct electricity. And they come in three forms. There are the strong electrolytes, which conduct electricity very, very well. There are the weak electrolytes, which conduct electricity, but they do so a little bit less well than others. And then there are the non-electrolytes, the ones that don't conduct electricity at all. And so the first thing that we're going to do this afternoon is we're just going to take a couple of minutes and just talk about the differences between those three classes and really what sets one class apart from the other. And so when we look at strong electrolytes will conduct electricity really well. And the primary reason they do is because there are lots of free ions in those solutions that allow the electric charge to move. Now, what are some common examples of these kinds of electrolytes? Well, pretty much any solution that has a dissolved salt in it is going to be a strong electrolyte. In addition to dissolved salts, any strongly basic or strongly acidic solution will also exhibit strong electrolytic behavior. Now, we didn't talk about the difference between strong acids and strong bases, weak acids and weak bases. We didn't talk about those differences in our discussion on Wednesday. And the main purpose there is that conversation isn't super important to us right now. When we talk about acids and bases as a general kind of class after midterm break, we'll get into what those differences are and why those differences are important. But for right now, we just think strong bases and strong acids split up into a lot of ions. Weak acids and weak bases split up into a few ions. And that's really the large difference between a strong electrolyte and a weak electrolyte is the strength of the acid or the base that is making up the solution. So in the weak electrolyte category, we're only going to find solutions of weak acids and weak bases. That's all we're going to find there. And again, the primary difference between the strong and the weak is the number of ions that are produced by those solutions. So the single factor that separates a strong acid from a weak acid is how many ions it produces when it dissolves. More ions mean stronger electrolyte. Now, when we start getting into the technical kind of components of this, we can start talking about, well, weak acids exist in an equilibrium. Weak bases exist in equilibrium. Really what that means is that unlike other reactions we've mostly talked about, where a reaction is one way, reactants turn into products and there's no reversing it, equilibrium reactions like these are reversible, in fact. And the reaction actually goes in both directions. So my acetic acid compound here on the left breaks apart into ions, but the ions also come back together to reform the acetic acid molecule that they came from. And so the solution actually has all three of those present at the same time. And that's why it doesn't conduct electricity as well, because some of those ions don't stay ions. They go back to making molecules. Whereas in a strong acid, if I were to look at the chemical equation of a strong acid, what I would see is something like H plus, excuse me, HCl, breaking down into H plus and Cl minus, and notice how that arrow looks. It's one way. All the HCl's are turning into H pluses and Cl minuses. None of the ions are going back to form HCl. It's a one-way street. So strong electrolytes, their reactions are one way. Weak electrolytes, the reactions are two-way. And as a result of that two-way reaction, we don't see as many ions present, so it doesn't conduct electricity as well. Non-electrolytes, on the other hand, these are usually molecular compounds, so not ionic. And they are substances that dissolve in water, but they don't break apart when they dissolve. So there are no ions in those solutions. And because there are no ions in those solutions, there's no conducting electricity, because you have to have ions to conduct electricity. And so those are the three classes. Now, what we will see in kind of summation here is that one very easy way to detect a strong electrolyte versus a weak electrolyte versus a non-electrolyte is to do a conductivity test. Now, there are lots of ways to do conductivity tests. There are probes that will do conductivity tests for you and let you know how well that solution conducts electricity or does not conduct electricity. There's also a really easy way to do it. The easy way is you take a light bulb and you create an open circuit. So you basically take the wires that would create the circuit for the lamp and you split them apart from each other. And you put those two ends into a solution and you see if the solution is able to complete the circuit for you. If it does, the light bulb lights. If it doesn't, the light bulb stays unlit. So this is an example of what that would look like. So in a strong conductor, what we see is that the light bulb lights very brightly. In a non-electrolyte, the light bulb doesn't light at all. And in a weak electrolyte, the light bulb lights, but you can see it's clearly a good bit dimmer than what we saw for the strong electrolyte. So that's electrolytes as this kind of broad class. Now, our main focus today isn't looking at electrolytes as this broad class. It's looking specifically at ionic compounds and taking a look at, will an ionic compound dissolve in water? Because if it dissolves in water, we know it's going to make a strong electrolyte. And that can be described using something called solubility rules. Now, the central idea of the solubility rules are these. Only certain kinds of ionic compounds are actually going to dissolve in water. Some are not. And while it can seem kind of random to think about which ones do and which ones don't, it actually comes out that there are three broad categories of solubility. And they are in descending order, meaning the first one is the most important, the most useful, then the second, then the third. So here are the guidelines that we want to follow. And we're going to start with the first group, the most important group, the ones that will always dissolve. So in the ion group that will always dissolve, what we have are nitrates. So if I have an ionic compound that is a nitrate, I know that it will dissolve in water. It doesn't matter what metal ion is attached to the nitrate. It can be silver, it can be iron, it can be potassium, it can be lead, it can be anything. That nitrate compound is going to dissolve in water. Same thing is true with acetates. Acetate solutions will always dissolve in water as well. On the cation side, any group 1 metal will also dissolve in water. So lithium, potassium, sodium, rubidium, cesium, any compounds containing those metal ions, they automatically will dissolve in water. In fact, if you start paying attention to the kinds of chemicals that we put out for you, when it comes to solutions, these ions always make the list. Why do these ions make the list? Because they're usually cheap to acquire and we know they dissolve really well. So group 1 ions, ammonium ions, these are ions that we would expect to dissolve in water, and they dissolve in water every time. No exceptions, no weird kind of rules associated with them, always the case. And that's why this rule is first. Because what it means is that if I see something that has one of these, I automatically know it's soluble. And as a soluble ionic compound, as a soluble salt, it is going to be a strong electrolyte. The second list are those that are usually soluble. Now, in this list, what we're going to find are there are 2 classes of ions, the halide ions, so chlorides, bromides, iodides, and sulfates. Most of these compounds will dissolve in water. There are a few exceptions in each case. So the exceptions that exist among the halides, silver, mercury 1, and lead 2. It's going to sound extremely corny when I say this, but an easy way to remember the exceptions here. For exceptions, we need to go to good old Merle. Merle's halides are insoluble. Now, who is Merle? Nobody. But if you look at how it's spelled, you can get the names of the 3 ions that are the exceptions. Mer for mercury, L for lead, S for silver. So Merle's halides are insoluble. Mercury, the lead, and the silver. For the sulfates, different sentence for you. The alkaline lead sulfates are insoluble. Why alkaline? Well, the calcium, strontium, and barium, where do we find those? Group 2, the alkaline earth metals. Lead, well, that's the other one. So the alkaline lead sulfates are insoluble. And so That's just a reminder for us that we're looking at group 2 and lead to find the sulfates that will not dissolve. But these are the only exceptions to those rules. So with the chlorides, everything dissolves except for those 3. That includes all of the other transition metals. That's your nickels, your irons, your zincs, you name it. Everything but mercury. And for your sulfates, same thing. Everything dissolves except for those 4. The alkaline leads. The third class is the opposite of this one. Instead of talking about things that are usually soluble, we're going to talk about things that are usually insoluble. And with the usually insoluble crew, almost everything is insoluble with just a couple of exceptions. Now, the most common exceptions on this list are going to be things that we've already talked about. So for like the sulfides, everything we've talked about thus far is an exception. So group 1, ammonium. Why are those exceptions? They're exceptions because they were in the first list. And the first list is more important than the other 2 lists. So if I have lithium sulfide, it doesn't matter that sulfides are usually insoluble. Lithium is always soluble. That wins. Same with the hydroxides. The only difference between those and these is that the sulfides and the hydroxides are also insoluble with group 2, not just group 1. Here's the other thing to draw out of this that's really important. The list that I'm giving you here is not an exhaustive list of all of the different ions that exist. Now, that's not meant to scare you or anything. That's just meant to kind of inform you. If you see something that's not on any of these slides, you can do 2 things. First of all, you can assume it's insoluble. And that only applies and is an exception if it's put with one of those always solubles. So think about that first slide. That first slide is an always, 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 always application. So if I have potassium and anything else, it's going to dissolve in water on the merits of the potassium. If I have ammonium and anything else, it's going to dissolve on the merits of the ammonium. But if it's not on any of our lists, we can assume that it's not going to dissolve. Now, your book summarizes these solubilities in terms of charts, puts them in table form in table 7.2. And so that is a good reference to have. In addition to that, what I will be giving you, I'll put it in the lecture prep folder for chapter 7. I have a 1-page document that lists out all these solubility rules in their kind of groupings, as well as gives you a list of strong acids and strong bases to look at. So I'll give you that so that you have kind of a 1-page reference that you can either print out or just have open next to your homework to help you kind of figure out the solubility kinds of stuff. where this is ultimately leading us is on Monday, we're going to talk about precipitation reactions, and we're going to mark how to track precipitation reactions using ionic and net ionic equations. And the thing that we need to pull, the thing that we need to get our head around before Monday is the idea of a precipitation reaction. Precipitation reaction is a reaction I put two solutions together and a solid form as a result. So we talked a little bit about these on Wednesday. We were talking about acid-base neutralization reactions and gas-forming reactions and redox reactions. This is another double replacement kind of reaction that takes place. And ultimately, what we're looking for out of these are solids. And so these solubility rules, what they allow us to do is they allow us to be predictive. So I can take a double replacement reaction. I can take a double replacement reaction, recognize that it's double replacement, because I got an ionic compound reacting with another ionic compound, and they're making two other ionic compounds on the other side. I can recognize that, and using the solubility rules, I can predict, oh, that's going to dissolve in water, that's going to dissolve in water, that's going to be a solid, that's not going to be a solid. And that's really important because what that allows us to do is it allows us to, because of that identification, because of that predictive power, I can start to identify my products. I can look at it and say, okay, based on the solubility rules, barium sulfate is insoluble. I see a white solid in my test tube. That must be the barium sulfate. And so this is what some of these kinds of reactions will ultimately look like. And this is where we're going ultimately on Monday. Is we're going to start learning how to break down those reactions and actually identify when a reaction takes place from the start. Go ahead and get your last point. And then once you answer that stoplight question, you're free to go for the day. Don't forget about the assignment due Sunday night in mastering, and start getting ready for that midterm. Have a good weekend.